Hi everyone, welcome back to my channel. So in this video, we'll be discussing a research paper that was released by Google DeepMind. It came out a few weeks ago and it's a very interesting paper. I even have the paper with me, but I'll be sharing my screen. We'll be breaking down everything to first principles and we'll understand things and it'll be a knowledge heavy session. So I hope you enjoy. Let's just get started. Let me share my screen. So yes. So the paper is called the Welcome to the Era of Experience. It's by David Silver and Richard Sutton. So David Silver has been almost a co-founder of DeepMind, and he's worked on products like the AlphaGo, AlphaProof, AlphaFold, which won the Nobel Prize. He's been one of the most active voices when it comes to the field of reinforcement learning. And Richard as Sutton, he's been like the father of modern reinforcement learning. He's been publishing such good research in the field of reinforcement learning for a long time. So when these two people publish something on reinforcement learning, we know it demands our attention. And David Silver, his lectures on reinforcement learning have been there on YouTube for the longest time, and they are really good. So feel free to check it out. So welcome to the era of experience, everyone. So as the paper says, what this paper is about is there is going to be a change, a fundamental change in how AI systems will learn. How AI systems will learn is going to change everything in the future. So, and that change is going to be from the era of learning from human data to the era of learning from experience, right? So let's just understand what does the paper mean by learning from the era of human data. So they're mostly like, take the example of a kid, right? Imagine you're teaching a child to solve math problems. You give them a worksheet full of addition and subtraction. For example, like learning subtraction or geometry, whatever. And for each problem, you show them the correct answer and how you got there. The child practices with these examples, learns the patterns and techniques, right? So this is like traditional human way of learning, kind of quite similar to how large language model learns. Like you show them billions of good quality examples of several tasks being performed, right? And that has done so good. Like you look at the performance of ChatGPT or any other LLM that you use, that is a product of like supervised learning to a good extent, where the model has been trained on input-output pairs, and look at the quality it produces, right? So, but the paper here, it gives a nudge that, however, while imitating humans is enough to reproduce many human capabilities to a competent level, this approach in isolation has not and likely cannot achieve superhuman intelligence across many important topics and tasks, right? So the paper is talking about something futuristic like superhuman, and it says that how can you assume superhuman capabilities when your learning is based on human data? So this is the point that the paper is trying to say. And it also says like LLMs right now, LLMs is sort of like the poster boy of era of learning from human data that this paper uses. So you'll find the example of LLMs recurring a lot in this discussion as we go through. So here the paper mentions one more thing, that LLMs have possibly scraped whatever the good quality information that is there on anything, any field that's there in the world right now. Take it mathematics, coding, and science, whatever knowledge has been extracted by LLMs. And now we are sort of hitting a limit, right? That's what the paper is hinting at. The human data is kind of the potential of human data is kind of getting tapped, and we are hitting that ceiling of human data. And that's why the paper hints at we need to transition from the learning from human data, because it is hitting a limit, to actually learning from this experience, what this paper is talking about. So now, first we understood what is this learning from human data, right? The child learning geometry, or when the child learns geometry, you show them quite a examples, right? Okay, to prove similarity of triangles, draw two triangles, put a perpendicular, and all that. And over time, the child sort of learns how gets a good intuition of of what to do when he gets a geometry problem, right? So you show them a lot of examples, or in the case of LLMs, output pairs, and now the child is ready to face the situation. He takes the exam, whatever. But now learning from experience, this is a new thing, right? So before we do that, let me make a brief and a good digression here. I hope you'll enjoy that, but it communicates our point. So let's just watch this.
It's my own fault for using PowerPoint. PowerPoint is boring. People learn in lots of different ways, but experience is the best teacher.
Yeah, so as we saw what the legendary Dwight said, so he was doing a fire drill and nobody read out his PowerPoint. So he actually he induced a fire in the office, and that's how people learn. So jokes apart, yeah, that's what the learning from experience is. When you are out there in the environment, just accumulating whatever you have learned, you're actually out there in the exam. Like after you've seen a lot of examples, you're actually out there giving the exam, right? So an example, let me give you an example that kind of illustrates what this learning from experience or reinforcement learning, what this paper calls, is all about. Imagine you're teaching the same child to ride a bike. You don't give them a step-by-step guide for every situation. Like, you don't give all of the good set of examples. Instead, you set them on a bike, explain the basics, like this is how you balance, this is how you pedal, this is where the brakes are, this is how you accelerate, like a simple set of steps. And now this child starts pedaling. He is out in the environment learning by himself. You have just provided him the basic steps, and now the child is out there in the environment cycling and thus updating what his knowledge about cycling. And that's how that's how we learn cycling, right? That's how we also as humans learn cycling. Somebody probably told us the basics. Now we're out there in environment. Maybe when we learn that, when we pedal smoothly, then we have to move forward. When something comes, we have to put the brakes. So these learnings are unique to us, right? And these learnings can only come when you are actually out in the environment learning. And this is what the paper is trying to hint at, because learning from experience is going to be the foundation of superhuman intelligence, or AGI, or whatever the world calls it, right? And reinforcement learning, or learning from experience, is going to shape that out, right? And so couple of few terms here when it comes to reinforcement learning here. We won't make it that technical. So the basic things like environment, which is basically the environment where you're actually doing your thing, where the cyclist, the kid is riding the cycle. The action steps that it could take would be pedaling, balancing, or steering, whatever we have told it to do. And the reward, like every RL system has a reward. So if you don't fall, so when we used to cycle, sometimes if we fall down, we probably know, okay, this time I pressed the brakes too hard and I fell down. Probably next time I won't do it again, right? So this is the reward that's provided to the reinforcement learning systems. And all by learning through this phase of being in the environment and updating our knowledge, reinforcing our knowledge based on the feedback we get from the environment, is what the era of experience is all about. Think of it like, to compare these two examples, learning from human data could be like the example of a parrot, right? A parrot, a brilliant mimicry artist, but learning from experience could be that of a dog, where the dog basically learns from humans, right? It knows the reward. If you tell it to do a certain thing, you probably give it a treat, and it won't do that thing again, right? And the paper also kind of talks about it. Like, for example, a dog learns entirely from experience, but human interaction is a part of its experience, right? So yeah, that's now the whole part. Now we have gotten a good understanding of what is the era of learning from human data is, and what is the era of learning from experience. So here in this paper right now, it provides very good examples of some of the learning from experiential learning products. What products have come out from the by learning through experience? One is AlphaProof, then AlphaFold, which won the Nobel Prize. And I want to dive deep into these examples because it'll strengthen our knowledge of how RL systems work. So I've prepared some notes here, and we will just get right into it. So AlphaProof, right? The paper you saw mentioned AlphaProof. So AlphaProof, what is it? It is basically for a given theorem, AlphaProof will tell you how to prove it, right? So initially it's trained on 100,000 human written proofs, and then it generated 100 million more proofs on its own, right? So first phase, it was trained in two phases. One is again that we see the era of learning through human data, which is supervised learning. And then the second one was reinforcement learning. So supervised learning, what happens, as we see, like the kid learning through examples, same. Think of it as a kid. You have shown them what the input is, what the output is, right? So here, for the one theorem could be, for any x belongs to real number, prove that x square is greater than 0. And then you give it a proof, some case-based approach. Assume x belongs to real number if x greater than 0, and so forth, right? Again, one more example could be proving Pythagoras theorem. So the theorem input is a square plus b square in a triangle. A square plus b square equal to c square in a right angle triangle. And then the steps could be draw square on each side, use similarity, and that's how you reach. So it has seen the complete phase of given an output, given an input, what's the output? It has seen that, right? And now comes the second part, which is it will actually be in the environment, and it will prove theorems on its own, right? So here, first things first, in getting slightly into the RL jargons here, where you have something called the toolbox of valid steps. So you basically define what are the steps that the RL agent can take in this situation. So here it could be make assumptions, as we saw, assume X is a real number, or apply number properties, or do case-based analysis. Actually, I had a PDF of this. Let me go to the PDF. I think that'll be much easier to read. So where was this? Yeah. So we were here, right? Yeah, so the learning process, right? So we define the toolbox of steps, which could be make assumptions, and this is quite exhaustive. In actual AlphaProof's training phase, or where it is actually learning from the environment, this will have a whole a huge number of steps that it can take, right? So now AlphaProof is actually there out in the environment, and it is actually using the steps that it has applied, right? So the starting part could be you provide AlphaProof, you give it the theorem, X belongs to real number, X square is greater than 0, right? For the first attempt, it is actually now in the environment, it is trying whatever we've defined it in the toolbox of valid steps. So it'll get something called, it'll try the first step could be assume X is belong to R. This is just for the example. The first step could even be consider the case when X is greater than 0. It could be anything, right? First, it'll check, okay, is this step there in our toolbox? Yes. Then the step is accepted. And then it'll check if this step leads to a reward, which is basically the theorem being proved. Reward in reinforcement learning terms is basically the outcome of your performed action. Similarly, a child, like when we are learning to bicycle, right? If we fall from the cycle, that's a negative reward. So if some action led to us falling from the bicycle, we'll probably won't do that action again. So the same thing kind of happens here. So if the action leads to it not being able to prove the theorem, it won't do it. It will reject and it'll start all over again. And it'll continue doing that. Maybe in the 99th time, it will get all of the steps right. And that's how reinforcement learning works. But there's a good chance it might not get right in the first time, or it will get right in the 8th or 9th time, right? So when it reaches a conclusion that it matches the theorem, the proof is complete. And it also sees what steps for a particular theorem led it to proving the theorem, right? So it analyzes, it gets which patterns lead to it proving the theorem. And one thing I would like to point out is, even in the case of supervised learning, large language models, as well as reinforcement learning, both of them are identifying patterns only. But the way they identify patterns is what makes all the difference. Large language models identify patterns by memorizing, basically, right? By seeing a lot of input-output examples, like it's there in your brain and then you apply it. Versus reinforcement learning identifies patterns by actually doing stuff. That's how it identifies patterns, and that makes it more stronger, because you immediately, when you see something is wrong, you immediately update your model weights, and then and that leads to better results. And that's the whole point what this paper is seeing, right? So I want to explain this concept deeply. So we'll see a couple of more examples to contrast how LLMs learn versus how reinforcement learning works. So how would the LLM approach this, right? So LLM also will see the input, it will see the output, and the LLM basically will think, okay, when I see a proof like, X belongs to R, proof X greater than 0, I should output a proof that follows this above pattern. And the pattern it could get, like, whenever there's a proof related to inequalities, which is in our case, use a case-based analysis, right? So this is why learning from memory is, like, it has seen millions of examples like this, and it probably could come to a conclusion that whenever there is something related to proving inequalities, I'll use a case-based approach, right? But there's a limitation to it. If the LLM hasn't seen enough examples of this specific theorem type, it might generate incorrect things, right? So that's why it's mimicking. It's not kind of getting a wholesome understanding of the topic at hand. Of course, when you increase on the volume, you can make it do it. But learning from feedback is much more beneficial, and it leads to a more novel way of learning. We'll see that right now. So AlphaProof now in the RL way, again, it'll see many different approaches, what works, what doesn't work. It can try, right? As I said, it'll first try this step. This step is there in the toolbox, X squared is greater than 0, so it'll work. It can also, as I said, it can try something blatantly different, right? Not just from the first X squared greater than 0. Suppose it tried this, and it is there in the valid toolbox of steps that it can perform, but it probably led to it not being able to prove the theorem. So it'll discard this step, right? Again, it tried something totally bizarre, x squared less than 0. It's not there in the toolbox at all. So it cannot, it fails, right? And yeah, so it tries a whole lot of other steps. And this phase in the RL learning is called exploration, and where it tries out all the different techniques that has been defined in its action toolbox of action steps that we saw earlier, right? And each attempt gets verified by a proving environment, which is called a reward. A reward meaning if it was able to prove, you get a 1. If it was not, you'll get a 0. And every stage, each step, if it leads to it proving the theorem, that step is further reinforced. So that's how it learns, by actually being in the environment. And one thing could be AlphaProof might discover that for this theorem, there's a simple proof. By the property of squares of real numbers are non-negative, therefore x squared is greater than 0, right? You see how novel this is? Because LLM, because it's learning from memory, it is basically just regurgitating what it has seen in its training set. Whereas the reinforcement learning agent could absolutely start from anywhere and then go about proving, and it can discover something totally novel, as you see here. By the it used this step, and it was able to just prove it in one line. And LLM would never generate this unless it had seen it in its training. But AlphaProof can discover it through experimental trial and error. So by the virtue of trying and failing, it is able to do novel things, right? Let's look at another example. For all real numbers x, 2x squared greater than 0. Again, LLM uses the same law, same thing it has learned through its pattern, that, okay, you see an inequality, use a case-based approach. And sure, it did it quite nicely. But it's not the most elegant solution, right? Through experiential learning, when it comes to reinforcement learning, by learning from experience, it can again do something quite novel. Assume x belongs to R, multiply 2 on both sides, and then square it, and then it's just able to prove, right? So the RL system discovered that case analysis is totally unnecessary for this problem. A simpler direct approach works, right? So as you see, this was novel, and this can be very much shorter than a couple of human written proofs, right? And this is what AlphaProof did. It was able to discover novel proofs to theorems which humanity had never seen. So this is what it did. And even in the game of Go, right? So what the RL system does is, let me just clarify, when we define the toolbox of steps, right? Here is when we define what all the actions the RL agent can take, right? I want you to remember that the RL agent can never go out of these set of actions that we define. It can play around with this. It can maybe do number 1 first, number 3 second, it can try out all the different combinations of what is defined in the toolbox of steps, and that's how it discovers something novel. Let me so don't think that RL can create something totally out of the blank, which is outside this toolbox of steps. It can play around with it. It can use different combinations of it, and then this is how it discovers anything novel. So let me point this out to the game of AlphaGo, right? Which I was talking about in the beginning, which David Silver and his team developed, which was a game that ended up defeating the Go champion, Lee Sedol. Go is a game that is quite famous in Asia, and AlphaGo was a RL agent developed by Google that ended up defeating the Lee Sedol, right? So here there was something called Move 37 that it developed, right? So Michael Redmond noted that AlphaGo's 19th stone move 37, was creative and unique. And this is what move 37 is, right? What I was pointing out, it is not something totally new. The RL agent came up with this discovery of move 37. No, when the RL system was designed for this game of Go, we again defined what all the steps it can take in the game of Go. Maybe go right, go diagonal, something like that. I don't know the game of Go, but it kind of played around with the combinations of whatever was defined in the toolbox of steps, and that's how it created something, a novel move called the move 37, right? So this is what I was trying to point out to, right? And yes, so another example where we will see, yes, the case of AlphaFold, which won the Nobel Prize, right? And I'm telling you this example because remember in the paper, in the first part of the paper, we saw where it said that the majority of high quality is hitting a limit in key domains. The data is hitting the limit, and human data alone is not enough, right? I want you to focus on this point because we'll uncover some interesting insights from what this section of the paper says, right? So let's look at AlphaFold. So AlphaFold is a RL agent that was developed by Google DeepMind, which ended up winning the Nobel Prize, right? And we will see what it did. Yes, let me just take a short break. Yeah. So AlphaFold, what AlphaFold did, it had a given sequence of a single dimensional amino acid sequence, and it was able to predict the 3D structure of what the amino acid will look like, right? So it predicted the 3D coordinates for each atom in the